So the first kinematic equation will relate velocity and acceleration to time. It says that the velocity at any moment, like right now, is the initial velocity, what it starts with, plus the acceleration times time. And this is only, all three of these equations only work when acceleration is constant. When we have something complicated, like a spring or something where it's always varying all the time, you can't use these equations. But for most of this semester, we can use these, or at least approximately use these. The second kinematic equation, that one relates position, initial velocity, and acceleration. And that says that the position at some moment, I'll just call that x, even though, so I'll write the equation down and then you'll see. That's position equals the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. Just a comment, nobody's bothered about using v for velocity. When I use x for position, that's fine. People feel like as long as I'm going side to side. If you're talking about something which is vertical, I would just change the spelling. So if it was up and down, I would call this y, and I would call this y initial. But the actual equation is really the same. So don't let the spelling of things bother you. Okay, so just a warning there. Okay, so that's the second kinematic equation. And then the third kinematic equation is the one with velocity squared. It's kind of an oddball in the way it looks. So this third one involves velocity at each moment in time, or each moment. It involves velocity at the beginning, the initial velocity. It involves the change in displacement, and it involves the acceleration, but it does not involve time. So that's why it might be useful. There might be some problems where they don't ask for you to find the time, they don't tell you the time. You don't need to find the time. This allows you to maybe solve things. So this one says that the velocity in one instant squared equals the initial velocity squared, that's why it's the velocity squared equation, plus 2 times the acceleration times the change in position, or you can just call that the displacement. Okay, so those are our three kinematic equations. Did you guys see these same equations in high school? Anybody remember seeing them in high school? Yeah, okay, quite a few. Some of you did, some of you didn't. Okay. These equations are what we will use. In high school, did you have a few other equations? Sometimes people learn a few other ones, which are just different combinations of these three. Okay, and really, this third one, if you watch the video, I explain how the third one is just a combination of the first two. So really, they're the first two. The rest of them are you just do an algebra to repackage them. I find that it is simpler if you limit yourself to 2 or 3 equations and get really good at understanding them, rather than having 6 equations and maybe not fully remembering them all, and then in the middle of a problem, it's like, if you want to solve a problem, you need to know your tools. And if you have too many tools, then it's hard to become an expert at any one of them. And I find that people end up getting kind of lost. They kind of like mix the equations up and whatever. Since all of them really boil down to the first two, we're just going to limit ourselves to these, and we'll work everything else out accordingly, using logic and algebra. I will put these equations on any exam that we have, basically the whole semester. So you will have these at your disposal and be given them on the exam. Other variations of these I won't give. So I would suggest, to get ready for an exam, use the tools that you will have at your disposal in that moment. So I would get used to using these and limiting yourself to these and using logic and math. Don't try to use a whole bunch of other equations you might find online. It's not that they're wrong. It's just they reduce to these and they won't be given to you on the test. So it's just good practice to do it this way. Questions about these? Did you have questions in the video? In class, people ask questions when I do the derivations. One of the things I find when I do derivations and stuff in the videos is, man, I get done a whole lot faster because there just aren't any. I explain it the way I think it should be done, and I don't have any questions about what I meant. So were there things in there that weren't clear to you? Just speak up if there were. No? Okay. I don't expect you to go through the derivations on an exam. That's just not that's not what this course is about. But I feel like to understand where things come from, you have to see that, sort of appreciate that. Okay, very good. So I'm going to give a problem. I'm going to just write the problem underneath so that you have the equations there to look at. All right. So you start from rest and then start from rest and accelerate at 2 meters per second squared. Just a comment. I'm telling you that it's an acceleration because I'm telling you the word accelerate. In problems, sometimes they will say, you undergo motion at 2 meters per second squared. They're not going to say the word acceleration. You would look at the units. So the units are your clue as to what that number means. Usually it means something, but you have to figure out what. Look at the units, okay? Start from at rest and accelerate at 2 meters per second squared for, let's just say, 3 seconds. Okay? What is your, I'm going to make a grocery list of things to find. What is delta x after 3 seconds? What is your final velocity after 3 seconds? And I know. What is your average velocity after 3 seconds? So average velocity over that whole time interval from 0 to 3 seconds. Okay, so take a second and see if you can figure these out. And then we'll do that. If you just logged on, the first little bit I was saying, so I'm going to do some problems today, just practice problems. If you had specific homework questions that you were struggling with, remember homework's due Wednesday, so tomorrow. I mean, I know you guys all got it done on Sunday, but anyways, just in case somebody didn't do it on Sunday night, homework's due tomorrow, and then there's another one on Friday. So if you had a specific homework question, we could work on that too. You could bring it up, and I won't do the whole problem, but I would, get you steered in the right direction. Okay. All right, so take a few seconds, work on this. I'll be right back, and then I'll have to give someone an eraser, and then
Who's first, Sean? You want it?
I don't know.
We heard John Paul's.
Oh, I was.
I'm thinking, no, that's just Sean. He don't care. Man. He's not talking to anybody important.
Well, we're doing our Zoom thing, but the online class is here. But they're just working on the problem. So, what's up?
I'm just on the list. Not really on the list, but it's a good thing. You don't want to be forgotten to do it.
So, okay, so these are the things that we know. So what we have to kind of lay out a path from the things we know to answer the questions we've been asked. So let's just take them one at a time. First one, delta x. So that would be the position at 3 seconds minus the initial position, the difference in position. Which of these equations, oh, and I've been given something about time, 3 seconds. So which of these equations involve position kind of stuff and time kind of stuff and maybe this other stuff that is just in we know? Equation 1, 2, or 3? Which one would involve, we want to somehow figure out positions. We know something about time and we know stuff about accelerations and initial velocity. Which equation, 1, 2, or 3 is going to help us there?
2.
2, right? Because 2 involves position kind of stuff, initial velocity, which I know, time, which I know, acceleration, which I know, and time, which I know. So 2 is going to be the one we want. So sometimes when I'm solving these problems, I'll even say, okay, to find delta x, I'll just lay out a path in my mind. I'm going to use kinematic equation 2, and that's going to allow me to find, it turns out I can find delta x from that. Okay? So I kind of lay it out in my mind, and then I do it. What happens is if I'm not clear, I sometimes get in a circle, right? There's an infinite amount of algebra you can do. Most of it's not helpful. So I want to make sure I have a plan so that I'm moving things forward, working towards my goal, right? So I'm going to write down kinematic.
Excuse me, Professor.
Mm-hmm.
It's kind of hard to see with that marker. It's hard to see on the Zoom.
Yes, thank you. I will switch. So I'm going from, I'll rewrite it. I'm going from, and just call me Sean. It's okay. Just say Sean. All right. Is that better?
Yeah, it's much better.
So to find delta x, the plan is to use kinematic equation number 2 and then arrange that to solve for delta x. And then plug in everything we have. So let's do that. Now I would do this stuff symbolically because when you start writing a whole bunch of decimal numbers, so like if I say, add up 3.64 and 2.71 minus 8.36, 421 times 87.327. If you just start doing it and you miss one, or you miss a decimal place, you forget the thousandth place and it's one of those numbers, you have to start over. And that's what happens in these physics problems. If you just dive into a bunch of numbers, type them all in, and you figure out you made a mistake, but once you typed it in, it all just kind of dissolves into that big pile of numbers, and you can't reverse engineer how to fix it. If you work things out symbolically, and you can check that those equations make sense, then at least you know that the damage can't be kind of further back than that. And so having those equations symbolically written give you a nice, it makes it easier to figure out where problems occur. All right, so let's write this equation down. Kinematic equation 2. And then I don't want x, I want delta x, which is x minus the initial position. The delta x is the displacement. So what I'm going to do is move this to the other side. Like that. And then this is nothing other than what I'm trying to find. This is, so I don't really care what x is, I don't care what x initial is. The problem asks me to find delta x. So good. And then I do a quick assessment. And I think through the knowns that I have. Do I know v initial? Check. Do I know time? Yes. That wouldn't matter because the initial velocity was 0, so this term just goes away. Do I know the acceleration? Check. I know the time. Check. I know everything. Now it's just a matter of plugging in and evaluating. So let's go through that. Delta x, just gonna, this equals 0 times 3 seconds, but it's just 0. Since you aren't here and you guys can't kind of like read my gestures, maybe it's better. I'm writing 0. A lot of times, once I see that this is 0, I just don't even write it. There's no point carrying it forward if it doesn't contribute. Plus 1/2, the acceleration was 2 meters per second squared times the time, which was 3 seconds squared. It is good to keep the units so that we can check. When we're done, we better get something with units of meters. Otherwise, it doesn't make sense as a position. So the 2's cancel. This gives me a factor of 9. And seconds squared. Seconds squared are going to cancel. Good. I'm going to be left with just meters. Okay. 9 meters. Raise your hand there, or I don't know, like use the hand thing to say if you got that same answer. Give a thumbs up if you did, or yeah, or you were physically, yeah. Okay. Some of you guys that don't have video on. Chloe, did you get that?
Yeah, I got it.
All right. Gavin? Put him on the spot. Priya?
I got it.
Okay. All right. Okay. That's how, should be a pretty easy one, but this process is how I will solve every one of these. I look at my knowns, I look at my unknowns, what I'm trying to find, I look at my equations, and I think to myself, I kind of say to myself, how can I combine these equations and the stuff I know to lay a path from beginning to end? And I pretty much will try to do that before I do any arithmetic. Let's try the next one. Hopefully you've got the knowns written down. The next thing we're trying to find is the velocity after 3 seconds. So velocity after 3 seconds, bring that down. Here are my knowns, and and I can add something now. I can add something to my list of knowns. I also now know delta x is 9 meters. So as you solve a big problem, your list of knowns will grow. That's good. Right? Once you determine something, you can use that going forward. All right. So I am trying to find the velocity after 3 seconds. How could I do that? Is there a kinematic equation which would allow me to determine the velocity after 3 seconds? Does anyone have an idea or how to proceed? No? All right, well, I'm looking for an equation that solves for velocity, and that's not initial velocity, that's just you call it the final velocity here, but it's the velocity at some later moment.
We use equation 1.
Okay, I could use equation 1. It turns out I could also use equation 3 now. Equation 3 doesn't involve time. Instead, it has delta x, which now is in my list of knowns. So if I wanted to, I could use equation 3. All right? So what I would suggest, I'm going to use equation 1 because it's linear. It's maybe a little easier, but it's faster to do. Well, we can do it. They're both pretty short, so I'll do it both ways, and we'll get the same answer. It won't matter. Okay. So to do this, the first path is going to be to use kinematic equation 1. And I know the initial velocity, I know the acceleration, I know the time, and use that to get the velocity. The alternate path will be to use kinematic equation 3 and the change in position, the displacement, which is now unknown. But anyways, let's do it this way. So I write it down, that's going to be V equals V initial plus AT. I know this, so I'm just going to go through, check my knowns and unknowns. I know this, I know this, I know this. It's a straight plug and chug. 0 plus the acceleration was 2 meters per second squared. Oh, made a mistake there. Gotta be careful. Times 3 seconds. And then I see that I only have 1 power of time there. I have 2 there, so that just becomes the first power, just seconds. And the meters just float through, and I get that the velocity after 3 seconds equals 6 meters per second. Okay. That's right. Just a comment. I have the same thing with my son's. My oldest son is in 7th grade, and they're doing some algebra kinds of problems. And one of the things that's tempting to do when solving problems, if you're used to, I don't know, figuring stuff out at home, you tend to like have scratch sheets, and you kind of just like little scraps of paper with little numbers and stuff written around. And I guess I'll tell you what I tell my son. Make each line a true statement. Okay, so line by line, make it a true statement. And the reason for that is, in the middle of a problem, if you get distracted and you look away, and then you retrain your eyes and you come back to where you were on that page, then the first thing you're going to do is like skim what was just written to reiterate what you're doing. And if that's a true statement, then you just pick up where you left off. What can happen is people will, sort of do like half simplifications, and then like they sort of do half in their head and half on the page, and then if you actually look at what's written, it's a jumble. And then that's kind of a dangerous problem solving strategy, because you end up mixing half true, half false statements. And if you're able to hold it all in your head, it's fine, and you get to the answer, no problem. But if you have to set the math down for a second and walk away and then come back, then it's a problem. So make each line a true statement. It only takes a second to just write that out, do it. And then it's clear to everyone and yourself what's happening. And if you set it down and come back to it tomorrow, you know where to start. Okay, did everyone get this? 6 seconds, or see how I got that? Okay, I'm gonna, just as an aside, use kinematic equation 3 very quickly, just to show that it works out. That one would say velocity squared is the initial velocity squared plus 2 times the acceleration times delta x. That would say that the velocity squared is 0 plus 2 times the acceleration of 2 meters per second squared times delta x, which was 9 meters. So that's going to be 2 times 9 is 36. And then I'll get meters squared per second squared. I'm just going to continue this over here. Velocity squared is 36 meters squared per second squared. This doesn't give me the velocity, it gives me the velocity squared. I have to take the square root. And when I do that, maybe you remember, when you take square roots, you could have plus or minus as a root. And so the answer here would be plus or minus 6 meters per second squared, or sorry, meters per second. You take the square root, the powers of 2 go away. And then you have to figure out, should you choose plus or minus? Because using this equation, both are consistent with that equation. We haven't made a mistake here. To get the right answer, you have to appeal to physics. Right? This equation doesn't know about v, it knows about v squared, which means that it doesn't really know about the minus sign that v could have. To figure that out, you have to think about it and say, oh, we started with 0 velocity and we had a positive acceleration. There's no way for the velocity to come out negative. So therefore, physically, we want the positive solution. So that's the kind of logic I would need to apply, a reasoning, kind of the physical reasoning of it. And that's how I get my answer. And notice they agree. So no matter how you do it, you're going to get to the same answer. Questions on that one? No? Boy, you guys are an easy crowd today. Wow. All right. The last thing I wanted you to find was the average velocity over those 3 seconds. Average velocity over those 3 seconds. Well, can I use one of these kinematic equations to find the average velocity? Do any of those kinematic equations have average velocity in them? I would say no. These V's are all instantaneous velocities. Instantaneous initial velocity, instantaneous velocity. So the average velocity doesn't appear in these equations. So you aren't going to directly use these equations, or you might have to indirectly, but not directly. For average velocity, let's go back to the definition. The definition of average velocity we had last week is that velocity average was the displacement over some time interval divided by the length of time. So that's going to be delta x over 3 seconds divided by delta t over 3 seconds. That was that's just the definition of what it means. So that's going to be change in position over 3 seconds divided by change in time. Well, my change in position, that's one of our results. That's the 9 meter number that we had. 9 meters. So this is going to be 9 meters divided by the change in time, which was 3 seconds, which is, well, 3 meters per second. Notice, what was the initial velocity? That was 0. What was the final velocity? 6 meters per second. And we said that we had a constant acceleration between them. So we kind of uniformly, steadily went from here to there. Well, maybe it's not surprising that the average was 3, right? Because if you average 6 and 0, you get 3. Okay. So that's a reasonable answer. All right. Okay? Everybody clear on that? Now, before we move on to another thing, or actually I'm going to ask more about homework questions to see if people have trouble with that. We've done the algebra part of this. Let's try to match this stuff with the graphs that we were talking about last week, or that we were talking about in lab, and we're going to talk more about in lab this week. Okay? So what I want you to do is try to construct a graph of acceleration versus time, velocity versus time, and position versus time. You can go ahead and just assume we start at x equals 0, just to make things simple. Okay, so take a second and try to work through these numbers, or use these numbers and things that we've talked about or learned about to construct acceleration versus time, velocity versus time, and position versus time graph. Okay, and I would do them in that order. That's just a little, that's how I would do it. Don't wait for me. I'm just killing time. Give you guys a chance to do this. So. Sometimes teaching is like when you're trying to get your kids to eat their dinner, you just have to outlast everybody. Okay, so let me start with acceleration. Acceleration versus time graph. So what I need to do, what I would do is maybe try to plot the acceleration at some different moments and just kind of connect the dots then. But it's particularly easy because we know that the acceleration is constant. And from math classes, we know that the graph of a constant is just going to be a horizontal line. So I just say, at time 0, what was the acceleration? It was 2 meters per second squared. So I put a dot. And after 1 second, the acceleration was 2. After 2 seconds, it was 2. After 3 seconds, it was 2. And then I would connect the dots. Okay. How many people got that or had that graph? Okay. Good. All right. What about velocity? Oh, I'm just going to follow the same idea here. The thing that will help me, well, lots of things help me. I have some numbers, right? So that's helpful. But I also want to try to remember on a velocity graph, what does the acceleration mean? And when from the velocity graph, what does change in displacement? Things like that. Those kind of map the relationships between velocity and position and acceleration on the different graphs. That's important here to help us. So for the velocity, I know that the initial velocity is 0. Okay, so I'll go ahead and put that one there. At time 0, the velocity was 0 because it started at rest. And then in this problem, we already solved for the final velocity after 3 seconds. We found that it was 6. So I'm just going to put a dot out here, and I'm just going to say that that is 6. Okay. So I know that after 3 seconds, the velocity is 6 meters per second. And then I think to myself, what is the relationship between the velocity versus time graph and acceleration? And so in particular, if you know the acceleration, what part of the velocity time graph do you know? Somebody tell me? That is, if you know the acceleration, what does that mean on the graph of velocity versus time? Someone call it out. It's okay if you don't. All right, so if you know the acceleration, that tells you the slope of the velocity time graph. So no, just an asterisk here. I think I can write it. Yeah, asterisk. Acceleration is the slope of velocity versus time. Okay? And if the slope, remember the acceleration was constant, so that means that the slope of velocity versus time graph is constant, and the shape with a constant slope is a line. So that means that I'm just going to have a line connecting these two. It won't be something complicated like a bendy curve or anything like that. Okay, so the slope of the velocity time graph has to be constant. So therefore, oh, sorry, hit my knuckles. It has to be a linear graph. So at any other point in time, the velocity is just going to linearly increase from 0 to 6. Is that okay? Raise your hand if that is okay. Was anyone able to get that on your own? Did you have the same kind of graph? Some people did. Good. Great. All right. Now, what about the position graph? I have the same kind of thing. Since I know lots about the velocity, I want to use that fact. I know that the velocity is the slope of position versus time, the graph of position versus time. An asterisk there too. Okay? So I'm going to use a very similar kind of reasoning to kind of feel my way through this curve. I said, assume that we start at x equals 0. I just threw that out so that it makes it easier to graph. So I'm going to say at time 0, assume we start at the origin. And let's see, what am I expecting? Well, I know the acceleration is positive. I should have also said that. That means that if you have an acceleration, the position graph won't be a line. It'll be a bendy curve. And if the acceleration is positive, that means the curvature, the way that it bends, is upwards. It'll be concave up. So I'm expecting something which is concave up. That's my intuition. More precisely, what I would do is I would go, and what I usually do is I take a few moments that I know something about, and then I kind of just smoothly connect them up. So I know that at the first moment, the position was 0, fine. And I know that the velocity at that first moment is 0. And I say to myself, well, velocity is the slope of the graph. So that means at the first moment, not only is the position 0, but the slope is also 0. I'm going to try to do that in red, and then, I don't know, hopefully it kind of works. So the slope here, is that visible at all? Madeline, is that okay? I don't know if you can see that at all. No?
You can see it like a little bit, but it's still kind of hard to see.
Okay, I just need for you to see a little bit, and then I'm going to draw it over it with blue.
Okay.
So I know that the slope should be 0 here because the velocity was 0. So the position is 0, and because the velocity is 0, the slope is 0. So whatever the shape is, it has to be kind of flat. Or not kind of, it has to be flat when it's here. And then when I get over to time equals 3, I know that the position is 9. So I'm just going to say, okay, so these are kind of flat, skewed graphs. I'm going to say that this is 9. I'm sorry that it's all bunched in here. Kind of. I'm going to say that at time equals 3, the position is 9. That's the height. And then I want to know, oh, what kind of slope should it have when time is 3? Well, I go to my velocity graph and I see that, oh, the velocity was 6. So that means the slope has to be positive. I mean, and if I drew things better, it'd be kind of steep even. But right now, but it definitely is upward sloped. So at the beginning, the slope is 0. At the end, the slope is positive. So I'd kind of hash in a little line like that. And then what I would do is well, one is I know the equation from kinematic equation 2, it's a parabola, all right? So it's got to go like that. But you also know we're expecting smooth kind of motions. And so I know that it's going to kind of smoothly connect between these. So I would just kind of go over it like that. And that would be my sketch of the motion. And that would be absolutely enough for full marks if I was grading it, because I'm not grading on artwork. But you have to connect the numbers of the problem to the graphs of the problem with enough detail that I can see that you understood what was going on. That's really the standard. Is it clear that you understood what was going on? All right. How many people had that kind of a graph? Okay, maybe not everyone. Was it the curvy part, the bendiness? Is that what threw you off? Okay. Do you see how I knew that it had to be curved? I mean, you can just look at the equation, fine. But really, it's because the velocity is changing, which means the slope has to change, which means it has to curve. That's how you know that. And to get that, I would go at key moments. You know, the initial velocity, or the final moment, and then sometimes if something's going up and down, like if I throw something, there the velocity would be positive, 0 at the top, and then negative when it started to fall. That top point would be a point that I would kind of sketch in there too. So in that case, I would want to get 3 points, and then I would just kind of, whatever, quickly connect them up in a reasonable way. All right, so maybe in the chat here, if you're kind of, can you let me know, like, just type in, if we're kind of ranking your confidence on this kind of a problem, are you feeling like 1 being not confident, 10 being confident? How many people feel like they're in the 1 to 3 range? How many people feel like they're in the 4 to 6 range, and then how many people feel like they're in the 7 to 10 range? So, okay. A few people feel like they're confident. If you're hiding behind not being visible, I'm going to pester you next time to figure out how you're feeling. So, have an answer when I ask you in class, in person. Okay. What I kind of went overkill on this one, but I think it's worth doing one, really, even though it's pretty easy, really beating it to death. We're going to do more and more of these. I'm going to, basically after we finish here, I'm just going to be recording videos between now and my next class. So I'll have some more examples online, more complicated ones, other kinds of questions you can have. So watch those. I think they'll help. The homework for Friday more than the one for Wednesday, I think, is mostly on average velocity and stuff like that. But the one for Friday is going to be using these equations more. So it has some trickier ones. Just a warning, if you haven't started, I believe, the other people who've done it, the homework for Wednesday doesn't take that long. The one for Friday's got some tricky questions, so don't leave it to the end. It will require some time. Okay. Are there questions on the homework for Wednesday or for Friday? So if you worked on them and got stuck, tell me, or we can try to go through some of them. Nobody?
I was able to finish them, but I did need help on, I think it was like the last one. Here, I'm gonna just pull it up real quick because I have it. I have it.
You tell me the
open.
number, I'll pull it up in my on my web browser, and everybody can look at it.
Okay.
The numbers may be different for everybody, but the problem will be the same. Up already.
I mean, I was able to get it done. It took me a while to finish it.
It's okay. I believe for Friday there's a hard one with planet. You're on a planet throwing something up in the air. But go ahead. Which is it for Wednesday's assignment or Friday's?
Yeah, it was for Wednesday.
For Wednesday, okay.
Oh, it was, for mine, it was number 4. It was the one with the gnat and the pencil.
Okay, I'll pull it up. And it's the same. The problems are not shuffled, so everyone's number 4 should be the same.
Okay.
So I'm going to share that, and everyone's numbers are different. You'll see my numbers, but that won't help you really. Just let me share screen, and okay, everyone should be able to see my sapling assignment. Is that correct? Yeah?
Yep.
Okay. All right, so a gnat takes off from one end of a pencil and flies around for so many seconds and lands on the other end of the same pencil. If the gnat flew a total distance of 5.65 meters, so that's like if the gnat was sort of leaving, what do they call those? Behind a jet plane. A chemtrail, right? Those streaks behind it. So if the gnat was leaving a chemtrail or a jet, like a streak behind it, and you were to kind of measure the length of the streak, and then it landed, the streak would have a length of 5.65 meters, and the pencil is, so it's 6 centimeters long, 0.0613 meters long. Find the gnat's average speed and the magnitude of the average velocity. So don't worry about minus signs, is what they're saying with that. Okay. So the average velocity, we've got a video on that, and we've talked about that. We haven't talked a lot about distance. I think there's one video where I went through what is average distance. The average distance is the total distance traveled over the total time. Whereas average velocity is the change in position, or the displacement divided by time. Okay? So to do the first one, to find the average speed, I would use the total distance. Remember, distance it's like what your car odometer reads. It never subtracts, it just keeps growing. So your total distance is going to be the big number. In my case, it's 5.65. I should have grabbed my thing. But if you do 5.65 and divide it by 32.1 seconds, that will give you the speed, the average speed. I believe them when they say it comes out to be 0.176. So it should be 5.65 divided by 32.1. If somebody has a calculator, here, I suppose in mind, 5.65 divided by 32.1, I get 0.176, which is what they're telling me is the correct average speed. And then for the displacement, I don't need to know anything about the middle. I just need to know the initial position and the final position and subtract them. And they tell me that I start on one end, I'll just call that 0 position, 0 meters. And then I land on the other end, which is 0.0613 meters. I'm just going to subtract final minus initial positions. That's going to be 0.0613 minus 0 divided by time. And again, I just use my calculator here, and I do 0.0613 divided by divided by 31.5 seconds. I can't remember. I have no memory. No, 30.32. Can't talk. 32.1 seconds. And I get 0.0019 plus change, 191, yeah, as my average velocity. Okay. Does that help, Madeline?
Yeah.
Okay.
Thanks for going over it.
Most of the time, really, like after this question, we will not talk about speed. Most of the questions are about velocity, velocity, velocity. Sometimes, though, they do want the average velocity. You have to remember that for average velocity, you look at the change in, well, it's what we have here. It's the change in displacement over time. To be honest, after this week, most of the questions are about instantaneous velocity more than average velocity. Other questions? Good question. That was a good one. Other questions? No? All right. We have like 2 minutes left according to the thing. So Madeline, you said you got it done. How long did it take you? Would you say hour, 2 hours?
Probably like an hour and 20 minutes.
Okay,
I
so
don't
more than
know.
an hour.
Just
Okay.
kind of depends.
So a little more than the last ones. The one for
Yeah.
Friday, it will take some time because some of those problems are a little tricky. In particular, there's one, if I remember right, there's one about you're on a planet and you're throwing something up in the air and then it's coming back down, and the acceleration due to the planets is different because they just have different masses and things. And the tricky thing on that is they don't give you enough information to use the equations and just get a number. But the question doesn't ask for that. What the question asks really is the ratio of how high the rock flies on the two planets. It doesn't ask for how high it goes on either planet. It wants the ratio between them. And I'll give you a hint. If the answer that it asks for is a ratio, the hint is set the problem up as a ratio from the beginning. And what will happen is the stuff you don't know just divides out. It's kind of like magic. And so rather than trying to find stuff, and in fact, in that one, you don't have enough information to find some of the numbers you want to find. But if you set it up as a ratio, all that stuff that you don't know kind of washes away, and you're left with just what you can do. So try it. We will, that's a hard one, right? It's hard. I know that every year people struggle with it. We will talk about it on Thursday, when we meet in person. I won't let you get out the door without talking about it. But don't put off your homework for Friday to the last minute. It does take time. Okay, I'll let you go. I forgot to send you guys an email with what I wanted for those videos. So I'll be posting it. It'll be due on Friday, and we'll make it some sort of little extra credit thing. But don't forget to do that either. All right. If you don't know what that was, I'll send the info in email so you'll know after that. All right. See you guys.